In Chapter 20, we will be focusing on carboxylic acids, but we will also take a look at some related compounds, including phenols. In this video, we're going to go over some general information on carboxylic acids and nitriles, including naming and structure and properties. When it comes to naming carboxylic acids, we can use the IUPAC name. And so instead of an alkane, we are going to replace the E with oic acid. So this first compound would be methanoic acid, ethanoic acid, propanoic acid, etc. And the IUPAC name is going to be very helpful when we start looking at acids that have different substitution. But for simple acids, the common names are going to be incredibly important. So the single carbon carboxylic acid, this is called formic acid. Next is acetic acid, and then propionic acid, and then butyric. This is the lovely compound that's responsible for the smell of rancid butter. 5 carbons, this is valeric acid, no comment. And 6 carbon, this is caproic acid, which is based on the name for goat, because apparently goats smell terrible, and it's because of caproic acid. So there's our fun connections with carboxylic acids. This we know as benzoic acid. This is the common name, and I couldn't tell you the systematic name if my life depended on it, so just know the common name. But we are going to come back to the systematic name once we start talking about acids with different substitutions. So here we've got 1, 2, 3 carbons, and so that would be propanoic acid. We don't have to specify where the acid is because that's got to be at carbon 1, but then this would be carbon 2, and so this is a hydroxyl group, so this compound is 2-hydroxypropanoic acid. Here we have 1, 2, 3, 4, so this would be butanoic is the base name. But we have an alkene between carbons 2 and 3, so that would make it 2-buteneoic acid. And we have a methyl group at carbon 3, so this would be 3-methyl 2-buteneoic acid. So bute tells us there's 4. Oic acid tells us it's a 4-carbon acid. The ene, 2-ene, tells us that there is an alkene starting at carbon 2 and then a methyl group at carbon 3. And the last example, okay, we have 1, 2, 3, 4, 5. So this is pentanoic as the base name. At carbon 2, we have a hydroxyl group. At 4, we have a methyl. And at 3, we have a ketone, but when we name it as a substituent, it is an oxo. And then we list the substituents in alphabetical order. So put this all together and we get, oh, I lied, it's not hydroxyl, it's hydroxy, 2-hydroxy, 4-methyl, 3-oxo, and then this should be oxopentanoic is one word, oxopentanoic acid. So carboxylic acids have priority over alkyl groups, over alkenes, alcohols, ketones, aldehydes, and there's rules. So know the basics, know the common names for the small carboxylic acids, know the common name for benzoic acids, and then be able to use the systematic name when it comes to other substituents. Now, when we look at carboxylic acids, it's important to think about the structure and bonding because that is going to help explain a lot of the properties. So we know that the carbon and the oxygen are both sp2 hybridized. And so we'll be talking about 120-degree bond angles. Normally, looking at our oxygen connected to 4 groups, we would assume that would be sp3 hybridized, but if instead this is sp2 hybridized, then there is a p orbital which can be in conjugation with the carbonyl. And so we can draw another resonance structure that looks like this. And there is a kind of an intermediate resonance structure that looks like this. And so the hybrid has double bond character between the carbon and the oxygen and double bond character between the carbon and the other oxygen, which is still connected to the hydrogen. And so the carbon has a big partial plus, but this oxygen also has a partial plus, and the carbonyl oxygen has a partial minus. So this can be seen in the structure because the carbon-oxygen double bond is a little bit longer than a typical carbon-oxygen double bond, and this bond is a little bit shorter than a typical carbon-oxygen bond. Now, as we think about the structure, let's compare this for a moment to a ketone or an aldehyde. Okay, so we're comparing a ketone or an aldehyde with a carboxylic acid. And based on inductive effect as well as resonance effect, this oxygen is going to be pulling away electron density from the carbon. And so in both cases, the oxygen takes on a partial minus and the carbon has a partial plus. But because this oxygen can donate some electron density by resonance, more so than the alkyl groups can donate electron density by inductive effect, then this partial plus is actually going to be spread out a little bit between the oxygen and the carbon. So this partial plus on the carbon is going to be smaller than the partial plus on a ketone or aldehyde carbon. In other words, a carboxylic acid, carbonyl carbon, is less reactive toward nucleophilic attack than what we've seen with aldehydes and ketones. Next, let's take a look at physical properties, and we want to compare different types of compounds with different types of intermolecular forces. So let's use compounds that are similar size. This is 72 grams per mole, 72, 74, 74. So this is about as close as we can get. The first compound will be held to other molecules of the same compound by dispersion forces, and this has a boiling point of 30 degrees Celsius. The second one, we have some dipole-dipole interactions. This has a boiling point of 80 degrees. The third one, the alcohol, we have hydrogen bonding. This has a boiling point of 99 degrees. And then the carboxylic acid, more hydrogen bonding, and this has a boiling point of 141. So the extra hydrogen bonding in a carboxylic acid makes these the strongest intramolecular forces compared to other types of compounds. And it's also possible to get dimers where your carboxylic acid is going to interact with, let's see if I can get this drawn right, another molecule of the carboxylic acid. And so this hydrogen has a partial plus, it's going to hang out with this oxygen with a partial minus. This hydrogen partial plus will hang out with this oxygen partial minus. And so dimers and higher aggregates are going to form, which is what leads to a higher boiling point than what we see in other similar molecular weight compounds. Now, what happens as we increase in size and we look at the boiling point? So this is 100, 118, 141, 164, 187, and 205. So we can see that the boiling point continues to increase as the molecule gets bigger, but it kind of becomes less about the carboxylic acid and more about the overall size of the molecule. So if we look at water solubility, when we are talking about formic acid, it is infinitely soluble in water, so it'll mix together in any ratio. And same thing with acetic acid, same thing with propanoic, same thing with butanoic acid. So all of these can hydrogen bond with water, and even though this part of the molecule can't hydrogen bond, it's still relatively small. But by the time we get to pentanoic acid, which has 5 carbons, now we see a decrease in water solubility. So this is only soluble to the extent of 5 grams in 100 mils of water. And the 6 carbon carboxylic acid, it's 1 gram per 100 mils. So yes, this part of the molecule is still capable of hydrogen bonding with water, but now we have so much R group that can't interact with water that the entire molecule becomes much less soluble.